Hello, this video is Measures of Spread Part 2. We're going to pick up where we left off in Part 1, and that's with z-scores. Who scored better on their test, a student who made an 1100 on their SAT or a student who made a 22 on their ACT? While the SAT score is definitely higher, 1100 is definitely greater than 22, what we really want to know is who did better with respect to the type of test they took. So if you have any idea about SAT and ACT, if you've either taken it or at least heard of the test, you may know that SAT score is scored in the, it has a high score. The highest score is in the thousands, and whereas an ACT score, I think the highest score is in the 30s. So it's scored much differently. So it's really hard to look at a score of 1100 and a score of 22. One being SAT, one being ACT, and knowing which score is actually better, because the scoring is completely different for both tests. So what we want to know again is who did better with respect to the type of test they took, and that's where z-scores come in. So we're going to use z-scores to figure that out. So what is a z-score? A z-score of a data value is the number of standard deviations away from the mean that data value is. So if you start at the mean and you go out to your data value, how many standard deviations does it take for you to get there? That's your z-score. Now, z-score has a formula. So z-score is equal to x. Now, x represents the data value that you want to find the z-score of, minus mu, which if you'll remember is population mean, divided by lowercase sigma, which is population standard deviation. When you do this formula, once you substitute in numbers, you want to do the subtraction first, followed by the division. Okay, subtract first, then divide. Okay, z-scores can be negative or they can be positive. So what happens, again, the z-score represents how far that number is in terms of standard deviations from the mean. So if it is above the mean, then it will be a positive z-score. If it's below the mean, it will be a negative z-score. If it is the mean, then that z-score will be 0. So z-scores can be negative and they can be positive. So here's an example, SAT or ACT. The national mean SAT score is 1083 with a standard deviation of 194. The national mean ACT score is 20.8 with a standard deviation of 4.8. Who did better relative to the type of test they took? A student who made an 1100 on their SAT or a student who made a 22 on their ACT? So we're going to, since these two tests are scored very different, we're going to use z-scores to figure out who did better. So first we're going to find the z-score for the SAT that was 1100. Okay, we're going to convert that to a z-score and see how far away that is from the mean. So if you remember the formula, the z-score for the SAT is, this was your x minus your mean. So the mean we found right here. Here's the mean. So 1100 minus 1083 is 17, and then we divide that by the standard deviation for the SAT scores, which is 194. 17 divided by 194 is 0.0876. Next, we want to find the z-score for the ACT. So again, we're going to do the score we're converting, which is 22, minus the mean. The mean of the ACT score is 20.8. So we're going to do 22 minus 20.8, and we're going to divide by the standard deviation of 4.8. So z-score of the ACT is 22 minus 20.8 over 4.8. 22 minus 20.8 is 1.2. When we divide by 4.8, we get 0.25. So who did better? Well, if we're looking at a number line, okay, the mean is 0. We'll put it right there. Here's 1. Okay, so if I want to, let me change the color here real quick. If I want to, oops, not that. If I want to figure out who did better, I'm going to look at I'm going to look at the number line and see which one is farther away from 0. And I still haven't changed my color. Bear with me. Okay, so 0.08 is really close right there. So this right here is the SAT score right there. And then 0.25, which is about, right, because I'm saying that this is a 1. So this is 0.25, this is 0.50, this is 0.75. So right here is the ACT score. So who did better? Well, the ACT score is farther away from the mean, which is 0. 0 as a z-score anyway. So ACT did better. So 25. So 0.25 is larger than 0.0876. It's farther above the mean in the score of the SAT. Therefore, the ACT score of 0.22 is better than the SAT score of 1100. So we're going to skip this example here. All right, let's skip to example 3. In the baseball team age data set from a previous example, we'll just say that. I think there's the data right there. Okay. It says find the z-scores that correspond to the following ages, 26 and 32. So I'm going to go back to example 2 real quick, even though we didn't work it, and it had us find the mean and the standard deviation. The standard deviation you need is the population standard deviation, so 5.97. The mean is 30.7. If you'd like to put this in your calculator and make sure you get the same thing, you can pause the video and do that now. But I'm pretty confident that 30.7 is the mean, 5.97 is the standard deviation. So I'm going to actually write that up here. The mean is 30.7 and the standard deviation was, I believe it was 5.97, yes. So let me write that 5.97. Okay, so now we want to find the z-scores for 26 and for 32. So the z-score for 26 is equal to the score, the data point that we're changing, which is 26, minus the mean, which is 30.7, divided by the standard deviation, which is 5.97. So I have my calculator on the side here. I'm not going to pull it up on the screen. I just want to do it over here by hand. Okay, 26 minus 30.7 is negative 4.7 divided by 5.97, which is negative 0.787. Again, they don't tell us how far to round, so 3 is usually good for z-scores. Okay, so this is a point. Let's see if I can make that point a little bigger so you can clearly see it. So negative 0.787. So now we're going to try and find the z-score for 32. So I'm going to change the color again. Alright, so the z-score for 32 is equal to the score I'm changing, which is 32, minus the mean, which is still 30.7, divided by the standard deviation of 5.97. So if we take our 32 and we subtract 30.7, we're going to get 1.3, and then we're going to divide that by 5.97, and we get 0.21775, etc., which we would round to 0.218. So what you'll notice is the z-score for 32, and my decimal keeps disappearing. 0.218 is the z-score for 32. Negative 0.787 is the z-score for 26, which means this is below the mean, which makes sense because it's less than the mean of 30.7, and this is greater. Okay, The next example is another SAT, ACT example. It says you score 550 on the SAT and 24 on the ACT. On which test do you have the better score relative to everyone else who took the test? So if you look at this table, they have the population mean and standard deviation for the SAT and the population mean and standard deviation for the ACT. So we're going to use those numbers here. Now they are different from the initial example we had, but that's okay. We're going to use it because this is what they're saying it is at this point. So first we're going to find the z-score for the SAT. So that score was 550 and the mean was 500. So minus 500 over the standard deviation, which is 100. So that's 50 over 100, which is basically 1/2 or 0.5. Okay, so now we need to find the z-score for the ACT. So z-score for the ACT is the score on the ACT, which is 24, minus the mean, which is 18. Sorry for that line there. And then divide that by the standard deviation. So 24 minus 18, I believe, is 6, and 6 divided by 6 is 1. Okay, so who did better? The ACT did better again this time, because a z-score of 1 is farther away from the center, from the mean, than a z-score of 0.5. So the ACT score was better. All right, so again, we're going to pause the video here. We're going to stop it here, part 2, and where it says bell-shaped histogram on the PowerPoint, if you're following along with that. And we'll pick back up the bell-shaped histograms in part 3.